Hello and welcome everyone. So I'll be explaining problem A and problem B of recent Codeforces round 707 div 2. Let's talk about problem B first. Problem B, naming Napoleon cake. So the thing is, let me dive into the actual statement rather than just explaining this. So the thing is that you're given an array of n integers, and inside that array there is going to be each and every element can be from 0 till n. Okay, element of value can be from 0 till n, and let's take this example 0 3 0 0 1 3. Okay, so 0 3 0 0 1 3. You could I could denote it as something like this. You will traverse the area. Okay, if you find any element which has a value greater than 0, what you will do is you will just color the indices itself and the other two back. Okay, similarly here we found an array element of only one value of only one, which means this value included and the rest of the elements which are going to be colored. Similarly, if I say that AI is equal to 3, which means that yes, this indices you will color it, and also the just the immediate two elements, like you could say it like a suffix part that you were going to be coloring. Okay, so and finally if you color a space, then you will denote it as 1. So if I say for this array the answer is going to be something like this. Okay, here we've got 3. Now I will definitely color this space, also the backspace, since there is no other suffix area here, so I don't have to color anything. So yet this would be the result, and okay, 0, so I don't have to do anything. 0, I don't have to do anything. Here comes 1. If it comes 1, then I know that obviously this space is going to be colored with 1, and here comes 3. So if it comes 3, what will happen? I will color this part, and also then I would left 3 minus 1 will be 2 indexes. So suffix from the suffix part, just color it. It doesn't matter if it overlaps the colored index, because at the end of the outputting, when you're going to be outputting the answer, you're gonna only have to answer whether it is colored or not. So you don't have to worry if it's over colored. Okay, any index. So if there's 3, then you will do what? You will color this index, and this index. Okay, just the suffix 1, suffix 3. So you will color this, and also if it's 0, okay, but I have already colored this. Okay, so as you can see, the statement explains clearly about what we're going to have to do, what we have to do actually. Well, you can do this in n squared time. That's pretty easy if you see, but that won't actually satisfy the time complexity here. So you have to find something in some way to do it in big of N. Okay, so the way that we could do this operation and finally outputting the answer whether some index is colored or not, you could use a Scanline algorithm. Now, what is a Scanline algorithm? I will put a link in the description. It's a basic algorithm where you can find the resultant value from some index to some other index consecutively, that which of the players, or which of the, like if you want to count something for that purpose, if you want to count something in some subarray type, or let's say if some sub-arrays overlap or something like that, and you want to know which of them does overlap, or which of them is colored and which of them are not colored, and you're taking it in a query, like if you're given a query and like L and R, and you will just color some elements inside that. Now if you do in a naive way, that might take you q times n complexity, but if you follow that algorithm, as I called the Scanline algorithm, then you might find it very efficient to do that. Now I'm not going to explain the algorithm. You might check in the description below, but I will tell you the approach how I did it. Okay, so let's take you to the code part. You will understand that when as you can see, the answer is 110 111. Okay, similarly everything is going just like this, but if I show you the code here and explain through the code how the Scanline algorithm is worked here. Okay, so first we actually took n, and then took actually this is from problem A, sorry, now it's problem B here. We took a resultant array, initializing each and every value 0, and then iterating from 1 till n, taking the AI value, okay, and now what I did here was, let me explain you here. Okay, let's take the same example. Okay, let's take this big example and explain everything. So I've got 10 elements, 0 0 0 1 0 5. Okay, so 0 0 0 1 0 5 1 0 5 and 000 and then a 2. Okay, so if I denote the index as 1 2 3 4 and 5 and 6 7 8 9 and then 10. Okay, excuse me. Okay, so we have just denoted the index, and let's try to find out how we actually did the solution in big of n rather than doing it in big of n squared solution. Okay, now the thing that I did was, I'm taking, when I see some value I, and if I see that it's greater than 0, then what I do is I go to the distant index where it actually starts from, actually ends coloring in a suffix manner. If I say, I think you will understand here more. Let's assume that this is 2, then you will understand more. Okay, this is 2. Okay, so I know that this is 2. Okay, when I find when I will find that this is 2, I will go to, I would know where will be my ending destination from the suffix point of view. So it's 4. Okay, then I know that it's 3. So how am I going to find out? 4 minus 2 plus 1. 4 minus 2 plus 1 is going to give me, 4 minus 2 means 2, 2 plus 1 is 3. So this is my starting index from the prefix point of view, and 3 and 4, these are the groups that's going to be involved in coloring. So as you can see, I can characterize this problem with the query problem that I told you, which we do actually basically in Scanline algorithm. Basically we're just coloring this portion, and in order to color this portion I don't have to go through all of it at that time. What I can do is I can do something like this. Okay, this is my, let's assume that this is my segment L and R. Then what I'm gonna be doing is simply like this. I had an array, I told you that it was res, and what I'm gonna be doing is res of 3 plus plus and res of 5 minus minus. Why am I doing this? Simply, it's the rule of the Scanline algorithm. When you see it, you will understand that. I will put the link in the description. So what basically these two lines are doing is they are making sure that I am covering all the areas from 3 till 4. Okay, now res 5 minus minus is actually indicating this. Yes, till 4, from 3 till 4 I have covered something, and to keep one sign of it, I am actually adding just one instance from where the group starts, which is from the left point of view, just like that. Now, how is this going to help us help us after that? I'll show you. But first, we're going to be building this array. Each and every index, if it's greater than 0, what I'm going to do? Look, it's 6. At 6th index, I'm finding the value as 5, so I will move to 6 minus 5 plus 1, which is what? 2 in index number 2, which means I've got one other array 2, so I've got one other segments from 2 till 6, and I'm gonna color it. Okay, color it to 1 or something like that. It doesn't matter if it's over colored, because we're gonna have to output 1 or 0 if it's colored or it's not. So for this point of view, I will do this simply like this: res of 2 plus plus, res of 2 plus plus, and res of 7 minus minus. I hope you get that. Res of 7 minus minus. Okay, res of 7 minus minus. So in this manner, I will initially characterize my res value, but after that I have to do one more thing to make sure to output the final result, which is I will try to find out the prefix sum and add all of those values inside the res. I hope you know how to find out the prefix sum, which is simply res I equal to res I plus res I minus 1. I mean by adding the previous prefix sums to the current sum and adding it to together. With this way, all the minus that we did, all the minus operations, the minus operation, they will eradicate. Okay, they will erase by, and it will eventually give us the correct result. And from that result, the values which are not 0, it's gonna be we're gonna output at 1 is which are 0, it's gonna be 0 basically. So if I take you to the code here actually I'm checking whether the index that's gonna be subtracted, or our starting operation, whether it's less than of 1 or not. If it's less than or 1, then we know that we don't have that much of index anymore. We have much more smaller than that, which is id is less than or equal to 1. That's just a basic checking here, but this is the main part. Okay, res there you go. This is for the id if id is less than 1. Okay, so if id is less than 1, I know that I don't have any id less than 1, so my starting point of view will be start from res of id of 1. But if it's greater than or equal to id of 1, I know what I have to do. Res of id plus plus, and now id is what? Id is exactly what I told you, a minus b. I minus ai plus 1, which is the ending from suffix point of view and the starting from prefix point of view. So after that, I'm gonna be doing the same thing that I do generally in Scanline algorithm. We do, and after that, just trying to find out the prefix of all the res values, and then checking out whether res value is non-zero or 0. If it's 0, then the answer is 0. If it's non-zero, then the answer is 1, because no matter what happens, I have to output if it's colored or not over colored or something like that. Okay, I hope you get that. Now let's talk about problem A. So basically, I'm not gonna dive into the question, I'll just tell you what I have to do. Basically, there are n stations and you are currently at moment 0. What you have to do is when you have to reach the station number n by traveling from station number 1 till n. Okay, and after all the journey, you have to find out what is the moment, when is the moment, and what is exactly that moment when you arrive at the station number n. But during this whole journey, we're going to have to do some of the operations that they have given. Now, what are those operations? They have told us that for each and every station there's going to be two indexes. Two instances of those index, which is one is their arrival time of the train, and the other one is the launching time of the train. Okay, the departure time of the train. So this is for each and every index. I'm gonna have a pair value like, okay, AI and BI. AI denoting the arrival portion, and the departure option is going to be referring to the value BI. And also one thing to notice is that between the index ith station and the I+1th station, when a train leaves from I till I+1, it's obviously gonna take some time in between that, and that time is the extra time, which is TM1. Okay, TM1, and this is the extra time when the train needs which the train needs to travel from I-1 to I. And so if we say formally, then the train needs to exactly move AI minus BI-1 plus TMI, trying to travel from I-1 till I. Now I-1 till I-1 till I. So this is the extra part, which is the departure, from the previous point and the arrival time of the current point. And we will also add the extra time that was used between those time. So that's how we're going to be calculating the total time from some index to the next index that we. So this is for this time is definitely for that. Now now there's one condition that that I have to make sure, which is when a train comes to a station, it will always wait for at least, let's say the station came to ith station, the train came to ith station, then it will wait for at least BI minus AI divided by 2 rounded up scale up units of time. And after that, if the current time is greater than or equal to BI, which is the departure time of that current station, then the train will leave. Okay, now in this problem we don't have to, we just have to do what they're saying, but we also have to make sure one thing, which is just a condition that we need to check, which is assume that a train comes to a station, which is the ith station, and as they have told us that you will have to wait at least this unit of time. What we'll do is we will add this time, because obviously the train will definitely have to wait at least this amount of time. We will add this time. Okay, after adding this time, this extra time, okay, which is the train is gonna wait for at least that time. Now after that, if that time is still less than the departure time of the train of the ith station, then my new time will always be BI. Why is that? They have told us if after spending the extra time and all of that, if the current time is less than BI, it doesn't matter if it counts or not, because at the end of the day you will move when the departure time is BI or greater than or equal to BI. For that case. What if for that case, which case what I told you is if that time is less than of BI or less than or equal to BI. Okay, so less than BI, sorry. If it's less than BI, you have to wait till BI. So then my current new result will be always BI. What if after adding that extra at least minute that the train is gonna stop on that station, if that time exceeds the time limit of the departure of the ith station, then we will have to then we will have to just simply stay on our track and making it sure that this is our answer, not any bi, because that value has already exceeded bi. So I won't change that value to bi, which means my final value won't change, my final time won't change to bi. It will be as it was by adding those values. To depict in the picture, I will tell you that you have to do something like this. Let's say this is one station and you have come to this station, and this station has a let's say this is the whole station, okay, the whole station. This is the arrival time and this is the departure time. Now this is your total time. Suppose this is your total time. This is indicating the total time. Now you know that, okay, I also have to add one thing, which is the extra time. The extra time the train's gonna stop. Let's add extra time to that total time. Extra. Okay. Now after adding that extra time, if this value, this point also stays between A and B, then your total result will convert to BI. Because no matter what happens, if you're less than BI, then you have to go from BI. That's the departure time. That's the way it is. But if that value, by adding extra, if that value exceeds the BI itself, then you don't have to convert it to BI. You just have to go the way you were going, taking the total time like this. Okay, I hope you get that. But let me tell you in the code more about it. This is problem A. Okay, so in that problem, what I took was the test case here, and then n and those values, taking the pairwise, you know, arrival and departure. This is the extra time, the travel, which is the travel time. You could say the travel time between indices I and I minus 1. Okay, and this is the fun part here. And this part is actually finding out the floor. The seal value, which is the extra seal value time. This is the extra time. This is for the extra time, and this is the distance total time. If you want to travel from I minus 1 till I, how many times that you have used till then, which is AI minus BI minus 1 plus TMI, which is the this is the travel time. This is that that difference between the current arrival and the previous station's departure. This is the total travel time from that consecutive portion, and this is the extra time that the train's gonna stay, which we're gonna be adding. Also, I have to make you have to make sure that you allow your loops this form of operation only from 1 till n minus 1, because remember, you are actually outputting the arrival time when you're going to be arriving in I equal to n. So if I is less than n, okay, if I is from 1 till n minus 1, only then you're going to be adding the extra time, otherwise not. So that's what you have to make sure when you code, and finally you're going to be outputting the answer. That's the way it is. That's the way you're going to have to do this problem. I hope I made you understand that. Till next time, goodbye.